Hello, today I'm going to share with you the results of our paper, Finger Spreading and Swim Speed. My name is Isra Alsahli, and this is a co-authored paper with my brother Alsahli. We are from Sir Winston Churchill Secondary School, Ontario, Canada. Let me start with a question. Do you swim with your fingers closed or open? Until recently, I myself always kept my fingers closed. This is a common and intuitive practice. We need to push water to move forward. So if our fingers are open, water will leak through and we might not have a strong enough push. We see examples of this principle in many places. Animals that are good swimmers have webbed feet. In engineering, oars have no gaps so we can push water easily. In addition to what we observe, swimming with fingers all closed can also be explained by the principle of physics. For every action, there is an equal and opposite reaction. This is Newton's third law of motion. We need water resistance to push forward in swimming. And if all our fingers are open, water will pass through easily and there will be little resistance. We get the most resistance when we keep our fingers closed. So we have good reason to think that keeping our fingers closed is the most efficient, as it would give us maximum resistance. What about research studies? Swimming is a popular sport and there are lots of studies focusing on how to swim faster. These include papers examining arm position, thumb position, and different hand orientations. The first paper to look at finger spreading and swim speed is Scheidhoff 1979. Their experiment used models of a hand dragged through a water tank. There were sensors attached to the hand model to measure forces around it. In that paper, they didn't find any significant advantage in spreading fingers compared to keeping fingers closed. After that first paper, there was not much interest in finger spreading until the early 2000s, when it was often observed that successful competitive swimmers swam with their fingers slightly open. For example, this is Ian Thorpe, a retired Australian swimmer who has won 5 Olympic gold medals. He specialized in freestyle swimming. Notice that his fingers are open slightly in this picture. Because top swimmers were seen swimming with their fingers slightly open, the question of optimal degrees of finger spreading was re-examined in literature. In this table, I summarized the studies that address the question. The columns show the methods used in the study, and the rows show their findings. As you can see, in the top right, the first paper, Scheidhoff 1979, used a physical model, and the results were inconclusive. Newer studies that follow tend to use computational fluid dynamics, CFD, which is a numerical approach. They use a computational software to visualize the flow of water and to calculate the forces generated by the model in their simulations. There are 4 papers using CFD that report that a small degree of finger spreading is optimal. We found only 1 paper reporting in favor of closed fingers, and they also use CFD. But how can it be possible that spread fingers can be better than closed fingers? What about Newton's third law of motion that we talked about earlier? Well, when fingers are spread slightly, it's difficult for water molecules to push through the gaps in the hand. Since the gaps between the fingers are small and the hand is moving very quickly, the water molecules will begin to fight to pass through the gaps, creating turbulence. Eventually, water molecules cannot pass through the gaps, because the turbulence acts like an invisible web between the fingers. This effectively increases the surface area of the hand, which increases resistance and speed. The third law still applies, but it turns out that if the gaps are small enough, they can help increase resistance. Now, let's look at our experiment. We used real swimmers swimming in the pool. Based on our prior research, we expected to find that spreading fingers slightly will increase the speed. We stated that hypothesis in null form here. There is no difference in the average time to swim with different degrees of finger spreading. We compared 3 conditions. 0 degrees is when the fingers are all closed, 10 degrees is when the fingers are spread slightly, and 30 degrees is when they are open quite widely. This is how we conducted the experiment. Swimmers are registered and divided into groups of 1 to 3 people. They receive the letter of information for informed consent and fill in the initial survey. At the pool, a swimmer is called to the lane and the timer, who is one of the authors, tells the swimmer how much to spread fingers in that swim. As the swim starts, the timer walks along the side of the pool and records the time to swim 25 meters. This swimmer takes a break while the others swim. Once all the swimmers in the group have swum, the process is repeated. A round is completed when a swimmer swims in all three conditions. We have two methods of control to make sure that the swimmers spread their fingers correctly and consistently. One is a physical control, and the other is a visual control. The physical control uses a device that we designed to help make sure that the swimmers remain consistent with the degrees of finger spreading. I will show you the device on the next slide. Our concern with it is that there may be a possibility that the device affects the swim time because of the mass and surface area added by the device. The visual control uses no device, and it is more similar to an actual swim. There is no possible interference from the physical device. However, swimmers may not be able to keep a consistent degree of finger spreading throughout the experiment, although we think that this variation would be random and biased against our results. This is a picture of our physical control device. It is modified from a silicone toe separator. In the 0-degree condition, the swimmer wears the unmodified toe separator, which allows them to keep their fingers closed. In the other two conditions, we increase the thickness of the separator by adding silicone sleeves to the wall between the fingers. With the visual control, there is no device. Instead, we train the participants to understand the three conditions and observe that they spread their fingers correctly. Before going to the pool, one author shows each participant the finger position for 0 degrees, 10 degrees, and 30 degrees. The swimmers are quizzed to make sure they understand the condition. For the quiz, the swimmer goes to the other author and shows the finger spreading for each condition. They need to pass this quiz before going to the pool. This chart shows the swim time in seconds for all conditions. On the y-axis, you have the time in seconds from 10 to 60. On the x-axis, you have the number of rounds from 0 to 80. From 0 to 40 is the physical control, and from 41 to 80 is the visual control. Each round represents the swim time of the same swimmer. Looking at the legend, the orange dot represents 0 degrees, the gray dot represents 10 degrees, and the blue dot represents 30 degrees. You can see that the blue dots, which are 30 degrees, are often higher up than the orange and gray dots, which are 0 and 10 degrees. You can also notice that the gray dots, which is 10 degrees, are normally the lowest, but not always. For example, the orange dots are lowest in these rounds and these rounds. These graphs show the average time to swim in the three conditions. Here, for the visual control experiment, we can see that the mean is 31.88 for 30 degrees, which is larger than 31.02 for 0 degrees, and that the mean for 10 degrees was the shortest at 30.17. We can see the same pattern for the median. In the physical control experiment, there is also the same pattern, except that the median for 10 degrees is slightly larger than 0 degrees. So, we have established that the average for 30 degrees is greater than 0 degrees, and 0 degrees is greater than 10 degrees, but it's not enough to just look at averages. We also need to check for statistical significance. In this table, we show the results of the paired t-test of the sample means, which compare the differences in swim time of the same swimmer in the same round. Let's look at the first panel, the physical control experiment. The first column shows the difference of swim time between 30 degrees and 0 degrees. On average, 30 degrees takes 1.2493 seconds, with a standard error of 0.3236. That gives us the t-statistic of 3.8608. You can see that this is significant at both 5% and 10%. In fact, when you look at the p-value, we are almost 100% confident that the difference is greater than 0. Next, when we compare 0 degrees and 10 degrees, the result is less clear. The average difference is less, 0.5370 seconds, with a greater standard error. We have the t-stat of 1.5028, which is not significant at 5%, but is still significant at 10%. The p-value shows that we have an about 93% confidence level. We observed the same result for the visual control experiment. The difference between 30 degrees and 0 degrees is highly significant, but between 0 degrees and 10 degrees is about 94% confidence level. Finally, the last panel shows the test of all the combined data. Not surprisingly, the difference between 30 degrees and 0 degrees is highly significant, and now that we have more data points, the difference between 0 degrees and 10 degrees becomes significant at 5% as well. Based on the p-value, we are more than 98% confident that 10 degrees has a faster time than 0 degrees. The results from our experiment suggest that there is a statistically significant difference in swim time using different degrees of finger spreading. So, there is an optimal degree of finger spreading. From our experiment, we find that 10 degrees is better than 0 degrees, and 0 degrees is better than 30 degrees. On average, the difference is less than 1 second between 0 degrees and 10 degrees. This seems small, but in competitive swimming, a fraction of a second can make a difference. In the future, we would like to expand this experiment by having more swimmers, testing more conditions, and using a larger pool, maybe a 50-meter pool instead of 25. Special thanks to the anonymous IYRC reviewer, and thank you everyone for listening.